Yeah, just to introduce myself briefly, my name's Toby Cambray. I'm a director at Greengage, where we do mechanical and electrical design and building physics design, and moisture stuff. So that's kind of my main focus, and it's quite relevant to some of the topics we're talking about today, weirdly, which is a little bit counterintuitive almost when we think about these sort of hot places. But yeah, when you have hot and humid, that's yeah, that becomes quite important, as we shall see. Yeah, we're talking about fabric efficiency for mechanical cooling in hot, humid climates. So as Andy said, this is related to a project in Tanzania. This is House 5, which is part of a wider kind of project, the Eco Village, which is a children's home run by UK-based charity called Islamic Help. So there's a number of these sort of dwelling houses, which this one holds 10 children and 2 adults who look after them, and there's a school on site as well. And Andy designed this with Alan Clark and Huda El Sharif, and this was actually just occupied this year, although it's been more or less finished for a couple of years. So there's some interesting kind of learnings coming through from that already. It's designed around an entirely passive approach to thermal comfort and conditioning. So there's no heating or cooling at the moment, and there's no glass in the windows. There's just a security grille, a laser cut steel sort of panel, and insect mesh. And so it's designed for extremely high levels of natural ventilation, and there's a little opening, or large opening really, in the ceiling to try and generate some stack effect ventilation. The windows face into the prevailing wind, or at least that was the intention. And the building's designed to self-shade as much as possible. So yeah, nice deep overhangs and things on the eaves. And oh, I can't. Next slide, please, Andy.
Trying to just to be clear, that's Andy, as in Simmers Mills, as in Adele Mills as well. So Adele was part of the team.
Yeah. Yeah, so we've got a couple of summers of data and sort of experience from the building, although the children have only recently moved in. And the sort of passive cooling strategy appears to be working quite well. But there's sort of occasions where it sort of goes outside sort of comfort limits according to the data, and that might sort of change a little bit now it's occupied, and we can potentially start getting some sort of user survey information coming in, which will sort of inform that further as well. And yeah, particularly kind of interested in quality of sleep as a yeah, sort of metric or issue that we want to be sort of very cognizant of. Next slide, please. So here's the plan, just to give the layout. So north is down on this particular drawing.
3 sections. The left-hand block is basically an open dormitory for 10 children and a separate room for the mother, as they call her. But the dormitory area is subdivided by perforated walls. So the partition walls are partly solid with doors in, but they also contain quite a lot of lattice concrete blocks that are made to allow air to pass through. That's a very important feature of the building. Then the middle section, that large open plan area, that's a living area. So bottom right quarter is a sort of kitchen area, which they've now furnished. Bottom left is a sort of part of the living room, but also prayer mats. And then top left is a sofa area, and top right is a bit of multi-purpose area with sort of kitchen tables, which can also expand into dining tables and so on. And then you have these double door sets that, when opened, create quite a strong, well, a very strong flow of air across the building north to south. And then left to right or east to west, you have a sort of a highly ventilated corridor. So again, when those doors are open, you get quite a nice wind tunnel effect. In terms of ceiling openings, you have an opening of about, well, the whole hallway, in fact, in the dormitory area has monkey mesh, insect mesh, but it basically is open to the roof space above. And then in the living room area in the center, that central square between the columns is also open to the ceiling, again, protected with monkey mesh and insect mesh. And then the toilet block on the right, which importantly is on the leeward side of the wind. So predominantly the wind will come from the north or the east. That toilet block is on the far end there, for obvious reasons, because of smell and so on. And that toilet block is ventilated with high level perforated walls. And just as an interesting note, we have some composting sewage system coming off that toilet block, which we had some success with in 2017, 2018 on a test unit.
Okay, so this is a section through the building, so showing our deep overhangs and the structure of the roof, which we'll talk a bit more about. So there's no insulation in there at the moment, but it's highly ventilated to try and dissipate heat that is building up in there. So it's ventilated through the eaves and up through the gap of the apex there, and also through a hole in the ceiling for stack ventilation. You can also see here that the walls are just a single skin of blockwork, and we have a solid floor with a sort of coral type aggregate in the floor there. Next slide. So yeah, I guess the key question is this thing comfortable? And this is an important topic when we're trying to design something in these kinds of scenarios to be more comfortable. And thermal comfort is kind of complicated. So in the UK, it's kind of easier because we don't have to worry about the sort of extreme heat so much. The sun is sort of less strong, and we don't have the humidity to worry about. And when we add those other things in, it becomes sort of more demanding. And then particularly with passive house design, the sort of part of the philosophy of passive house design is to make achieving that comfort, some comfort, sort of as simple as possible. And we can, by doing the things that we do to the fabric, we can sort of forget about some of these things like the sort of airspeed as a result of air tightness, for example. But broadly speaking, the project's working pretty well so far. So next slide. So as I mentioned, ISO 7730, which is the standard that's sort of widely used and is incorporated implicitly sort of into passive house design, and doesn't directly account for sort of physiological and behavioural adaptation. And so it knows about physiological effects, but doesn't reflect the fact that if we spend long periods or grow up in hotter climates, that our bodies adapt somewhat to those kind of climates. There are other models available, as I say. So there's a number of models that take into account adaptive comfort, so the way our bodies adapt and the way we consciously or unconsciously adapt our behaviour to improve our thermal comfort. So within ASHRAE 55, there's a sort of a sub-model that accounts for that, and we have things like SIBSI TM59, which looks at the way the outdoor conditions influence the thermal comfort thresholds and parameters. But there's other aspects that are harder to integrate into our kind of our hard engineering models of thermal comfort. and because when we put people into our buildings, they often do weird things that mess up our careful calculations. So it's important to have that awareness as engineers that we're dealing with real people with their own preferences and things. But this is really important to kind of think about carefully, because a lot of our sort of design choices flow directly from the sort of philosophy that we choose of IPs. So this is some data that's been collected over the last years for the building. So this is for a factory thermal comfort model, and so here we have a temperature band of acceptable air temperatures, which varies with your daily mean temperature. So this is saying as it gets warmer outside, you can tolerate warmer conditions inside. And you can see that most of the time the measured conditions are within that band of comfort, which is good. Next slide. And this is just a alternative model, again showing that there's another version of the ASHRAE 55 model, again showing that the measured conditions, broadly speaking, are within that comfort band. And this particular model is actually showing that sometimes the space is actually a little bit too cool potentially, and so particularly overnight as a result of this highly ventilated strategy, when the night temperature drops, maybe we're getting uncomfortably cool. So there's an interesting kind of balance to strike here. My Zoom's just dropped out, so I can't see what I'm talking about, but I can look on my PowerPoint here. If we go to the next slide, Andy, I'll try and follow along home. So we should have a slide saying future and wider context.
Yeah, that is the slide.
Great. I'm sorry, everyone. This is frustrating. So if we're within these kind of comfort bounds most of the time, then that sort of begs the question is, why are we interested in mechanical cooling? And there's a couple of answers to that. So one is that it would be nice to be within those bounds all of the time, and to potentially do that by mechanical means. So that's a thing. Also, in the kind of wider context, with climate change, we can expect more extreme weather in all parts of the world. So it's likely to get warmer in Tanzania, which might sort of push us over those limits more often. So maybe active cooling is a sensible response to that. Also, throughout Tanzania and the region, and I would guess other parts of the world as well, there's a lot of poor design going on, particularly with some buildings that are kind of built to these sort of aspirational kind of Western aesthetics features, which aren't well adapted to the local climate and don't respond to the vernacular there. So with lots of glass, because that's a sort of aspirational thing that might not be properly shaded, and without this sort of idea of plenty of natural ventilation for free cooling. Next slide.
Okay.
So the kind of brief that Andy put to me was this sort of a series of questions and around what would it look like, and what would be the implications if we were to try and put mechanical cooling into a building like this, or this particular building. So one of the concepts that we were quite interested in is the idea of cool refuges. So not necessarily entire buildings or every building, but places where people can go in sort of particularly extreme weather. And so this is an idea that HUD has promoted within our group. So it might be a zone within dwelling, so the bedrooms in this case, or it could also be sort of community building where people gather And that's something that we sort of have seen, I think, in recent years in the UK. But with warm spaces where people can go if they're in fuel poverty, for example. So some of the other questions were how could the building have been designed better if we'd have had active cooling in mind at the beginning? How could the building be retrofitted to minimise demand and resilience from air conditioning? How would the building compare against the passive house KPIs? What's the sensible retrofit spec look like? So what could we practically do to the building? Next slide, please.
Okay.
Thinking about the way the ACB standards are structured now, are there kind of ways that we could group retrofit measures? Like a step one and onwards kind of arrangement as we have in the ACB retrofit standards. Are there any potential issues arising with the methods that we're using, and how could we resolve those? Mixed mode, so in time or in kind of space, as it were, so different times of the day, or maybe different times of the season, although Tanzania is pretty stable, they don't have a lot of seasonal variation. Or, as we were talking about, do we have just specific zones that receive mechanical cooling? Do we need to think about thermal bridges and condensation and mold risks for obvious reasons? And what other constraints might influence our design here? Next slide, please.
Okay.
Just as a bit of a spoiler, but to introduce an important concept that we're going to be talking about a lot today, a lot of it comes down to dehumidification load and the energy required to reduce not just the air temperature, but the humidity in the air. So I'm going to be talking about sensible and latent cooling quite a bit. So we'll just spend a minute unpacking that a bit. So from your GCSE science class, you might remember that the difference between sensible and latent cooling is basically the change in temperature and the energy required to change that temperature versus change in state. So going from a liquid to a gas, could also be a liquid to solid, but we're not talking about that today. So if I have a meter cubed of air or something and change the temperature of that from a glass of water in this case, the temperature just changes from 10 to 60 degrees, and that's a sensible change. Whereas if the temperature is the same and we change it from a liquid to a gas, so water vapor in this case, that's the energy required to make that change of state is latent energy. So in the context of air conditioning, sensible energy is the energy required to just change what we call the dry bulb temperature, or the temperature of the air, and the latent heat would be the energy required to change the moisture content, because we're talking about evaporating or condensing water out of the air. So slightly different in the context of air conditioning, but that's where that sort of comes from. So sensible is about just the air temperature, and latent is about changing the amount of moisture in the air and the energy required to do that. And we're interested in the moisture in the air because it has an effect on the thermal comfort, and because it's very humid, that inhibits the amount of heat that the body can lose via sweating. And if it's very humid, obviously, same as in the UK, then we might choose a mold risk if the humidity is high enough to allow mold to grow. So we need to be quite careful about humidity for these reasons. Next slide, please.
Okay.
So this is a psychometric chart, which some of you might be familiar with, and this is showing us a couple of things. So the coloured bands are bands of comfort, according to ISO 7730. And you can see here that the temperature, the thermal comfort depends not just on temperature but on humidity as well, and it also depends on some other stuff. So in particular, the airspeed. So for this graph, we've assumed it's 0.2, so quite low airspeed. CLO is the clothing factor. So that's just a kind of numerical representation of how many clothes you got on. Is it a big puffer jacket or just your undies? MET is the metabolic rate. So 1 is just for sort of you're sitting at your desk and working, maybe a little bit lower for sleeping, or potentially much higher if you're doing a workout in the gym or something. And the MRT is the mean radiant temperature, and that's quite important for other reasons we'll get into. You can see here that if we want to move down through the comfort bands from being too hot to a neutral or slightly warm state, then we need to sort of cross over the lines of not just temperature but humidity as well. And it turns out that we're sort of almost more interested in the latent cooling, so removing humidity from the air, as we are in the sensible cooling, as in just changing the temperature of the air. And it turns out that takes quite a lot of energy. So we also needed some weather inputs for the PHP. So we got some data from Meteonorm, and just to sort of sanity check that, we compared that with data that have been collected on site for the last year or so. And the temperature's pretty accurate, but Meteonorm seemed to be underestimating the humidity. That could just be the last year was a particularly humid one. It has been more rainy, I gather, the last year or so. That's the data we used. We're talking about the fact that we need to do lots of latent cooling. So if we consider just a meter cubed of air, then to change the temperature just by a couple of degrees, so from 30 degrees outside, which is typical kind of outdoor temperature in Tanzania, to 28 degrees, which was the number we picked for our sort of set point in PHP, and that's another thing that's sort of open to debate. It takes about 0.66 watt hours of energy to make that change in that 1 meter cubed of air. But if we take that same meter cubed of air and reduce its humidity from 88% at 30 degrees, 60% at 28 degrees, that means we need to remove 9.2 grams of moisture. But the latent heat of water is 627 watt hours per kilogram. So that means we need 5.8 watt hours to make that same change in humidity. So for that sort of air conditioning process of reducing the temperature and humidity, 90% of that energy required is going to be latent as opposed to sensible. So that sort of puts the more numbers that I was just talking through. So 90% of the energy required to condition the air as it comes in, not do anything else, just to condition that ventilating air. 90% of the energy goes into reducing the humidity effectively, only 10% into changing the temperature. Next slide, please.
Okay, yeah.
So we should have a little bar chart.
Correct, yeah.
So we're just adding to that same data now the internal gains of moisture. So we'll have a little bit of moisture generated internally from breathing. For this building, we don't need to worry about the cooking because that happens in a separate space. But yeah, basically we can assume that we have about 22 grams per hour per person. And if you sort of crunch these numbers through, we get to about 1.2 megawatt hours or 12 kilowatt hours per meter square per year. And the bar chart here is just showing that that's still quite a small proportion compared to the amount of moisture we need to remove from the air into the building just to avoid a high humidity in the air. So in other words, the moisture that we need to worry about is all in the outside air. It's only a small proportion of that is moisture that's released by people and their activities in the space. So next slide, please.
Okay, roof.
So the roof is quite an interesting one because that's where we're receiving the majority of our solar gains, and because it's pointing up towards the sky, the sun comes around quite high because we're near the equator. And unlike the UK, solar gains on opaque elements in Tanzania are really important, and we need to calculate those out and think about those quite carefully, which we don't normally need to worry too much about in the UK. And so those gains heating up the outside surfaces of the building find their way through and increase our cooling loads. And crucially, they increase our cooling rather than offsetting our heating, which is, so in the UK, we're more worried about heating typically, although overheating is definitely a problem that we need to think about as well. But in any case, when we are worried about the cooling, those gains are giving us a problem rather than helping us out with the heating. The nighttime losses are also quite significant, and that could potentially be helpful to lose heat to the sky overnight, particularly in this case because we're talking about a sleeping area, although that area could also potentially be used for sort of study and things as well. So that's sort of some complexities to kind of bear in mind. So as well as having an influence over the heat losses and heat gains and the space, the effect of that solar gain on the roof it has quite an important effect on the thermal comfort. And in simple terms, Peachtree is not the best tool for really calculating that out in a detailed kind of way. So it can sort of make an estimate, and that's helpful. But there's better tools available for doing those kinds of things. Next slide, please.
Solar heat gains via roof.
Okay, so this is an animated one, so I have to coordinate carefully, Andy.
Okay.
Just to kind of think through the physics of what's going on there, we've got airflow through the roof, shown by the blue arrow there, and if you click once, Andy.
Oh, sorry. Yes. Yeah. Sun radiation. Yeah.
Yeah. So we can see the red arrows is representing our sun directly on the roof. We'll also have indirect radiation from the sky, diffuse radiation coming onto the roof as well, which is significant. But when that radiation hits the roof, some of it will be reflected back, so you should see some slightly smaller red arrows.
Yeah, got that.
And anything that isn't reflected back is absorbed, kind of by definition, and that goes to heating up the surface of the roof, which is a corrugated metal roof in this building. And so we should see that red line, showing the roof heating up. Once that roof is hot, once it's hot, let's keep it simple, it will itself be start radiating more heat. So if you click NND, we can see that heat will be radiated from both sides potentially. So we're going to lose some heat up to the sky, but a proportion of that heat is also going to be radiated down onto our ceiling. So that's going to be a heat gain, but also it's going to heat up that ceiling, which is going to influence the thermal comfort. So the selection of kind of roof colour is quite important, and the relative proportions of reflection, absorption, and emission. So the emissivity value of the roof and different surfaces is quite important. So in theory, if we were able to tune those values, we could sort of optimise the performance of the roof to help as much solar radiation as possible bounce away. And there's companies I'm trying to get in touch with who have a range of coatings and things that are really helpful for these kinds of applications. So yeah, that's sort of an outline of the physics of what's going on with the roof, and which kind of gives us some clues about what we might do as a retrofit kind of measure. Next slide.
Okay, measurements from Tanzania.
Yeah, so we've got a thermal image here from another house on the site, House 3, which was designed with let's say less attention to the thermal comfort and performance, and this house doesn't have the sort of such a highly ventilated roof space, and you can see here the thermal the temperature on the ceiling there is getting pretty high, so often over 35 degrees, showing 38 here, whereas in House 5 it's more typically around 32. So that highly ventilated roof is certainly doing better than this one, but that 32 is still higher than we would like it for optimum thermal comfort, and because we perceive temperature as a sort of function of both the air temperature and the radiant temperature, or the temperature of the surfaces surrounding us. So if we can keep that ceiling temperature down, that's really helpful.
Just for context, it is useful to know that when I measured the 32 degrees on the ceiling, the walls were around about 30 in House 5. Just for context. Next slide. Great. Influence of radiant temperature.
So this is our psychometric chart again, and it's got the same crosshairs are at the same point, but we've got a slightly different mean radiant temperature in there. So we have 28 degrees, so a bit cooler than was measured, and then the 30 degrees, and you can see that basically shifts the bands of comfort from one side to the other. So where the ceiling or the mean radiant temperature is a bit cooler, the crosshairs are closer to that neutral space where we ideally want to be. Next slide.
Radiant discomfort.
So this is just a little section from ISO 7730, or thermal comfort standard, or one of the thermal comfort standards, and that's showing that basically that that thermal comfort is particularly sensitive to having an overheated ceiling. So the line is sort of steepest for warm ceiling. So we get this kind of double whammy of discomfort, because it's not just the fact that it's hot, it's the fact that it's asymmetrical, and so it's going to be warmer than our floor, for example. Next slide.
Okay, from MVHR to MVER.
So those of you that are familiar with passive house especially be pretty comfortable, hopefully, with MVHR as a concept. So when we're worried about humidity, whether that be in a sort of super cold climate where there's not much moisture in the air, or in this case where there's way too much or more than we'd like, we can start to think about a system that we call MVER, which stands for mechanical ventilation and enthalpy recovery. So normal MVHR obviously transfers heat from our stale kind of outgoing air into our cooler incoming air in the UK. We can use a similar trick in hot climates to transfer temperature, or heat rather, from the outgoing air, from the incoming air to the outgoing air. So we're going to use the cooler outgoing air to cool down, to pre-cool our incoming air. So I don't know, I just made up these acronyms, but you might call that MVCR, or mechanical ventilation with cooling recovery, or cool. I don't like that word, but cooling recovery. But that's only about 10% of the problem, as we saw in that pie chart earlier. So enthalpy recovery basically works by having vapor permeable sort of membranes or panels inside our plate heat exchanger, so that moisture can pass from one airstream to the other. So that's helpful, as I said, in very cold climates, so Canada and places like that. But we can also kind of recover dryness, which is what we're interested in here. So in this case, moisture will be transferred from the sort of over moist incoming air into the dry outgoing air. So we're going to dry out our incoming air, which is what we want. Next slide, please.
Disaggregation.
So that, yeah, thanks. So yeah, it turns out that technology is potentially really useful to keep our demands down. So this was the results from the sort of first pass of my sort of quick and dirty PHP model, and I sort of did a bit of hacking around to adapt this graph, which is in PHP but doesn't split out the dehumidification nodes, so I did a bit of fiddling around to get it to do that. And that's now showing us that we were to just install a split unit or a cooling into the building and run it sort of 24/7 to 28-degree set point, and we'd have an energy demand of about 300 kilowatt hours per square meter per year, which is a lot. So definitely worth doing something about that. And on the right-hand side, this is a bit different to the one that people are probably used to if you do passive house design in the UK. But it's a similar kind of idea. We've got our heat losses and heat loads, and they're a combination of sensible and latent in both sides. But the stuff on the right-hand side is kind of fabric-y things that we can potentially do something about. So our opaque solar loads we've talked about, and then our sort of latent loads are the three at the top there. And I've split those out here into infiltration loads. So dehumidification that's necessary because of air leaking into the building. Our internal loads, which are dehumidification loads as a result of breathing, cooking and stuff, and then dehumidification loads as a result of mechanical or intentional ventilation, and so that's the sort of necessary air for good air quality. So we can see that our opaque solar loads are sort of the biggest proportion, so most of that's from the roof, but some of it's through the walls as well. Sort of careful design of the roof and a bit of insulation and some attention to the emissivity and reflectivity of the roof is going to be really useful. And then the top chunk's really saying that basically making the building as airtight as possible and using this mechanical ventilation with enthalpy recovery is super handy as well. So if you plug that all into PHP and allow for a modest amount of insulation, we don't need that much actually, because the air temperature is the delta T is smaller than we have in the UK, so it's less hot than we are cold in the winter in the UK, if that makes sense. There's less of a temperature difference, so you don't need that much insulation, apart from in the roof potentially, where it's a bit different because of the solar gain. And if we assume we have our I'm mixing up my acronyms again here, but mechanical ventilation with coolth and dryness recovery, or MVER, and if we go hypothetically to a sort of super airtight building in line with passive house standard of 6 air changes, that really dramatically reduces our dehumidification loads. So those are the sort of the key things really to that solar protection, sort of modest improvements to the value, so a bit of insulation, and sort of super airtight and mechanical ventilation with cooling and dryness recovery is sort of the way to go with this. And if we do this according to this model, and it is just a sort of very simple high-level model at this stage, then we can reduce that by getting on for 3/4, but it's still quite high compared to sort of passive house criterion at 74.4 kilowatt hours per square meter of cooling demand. Next slide, please.
Okay, limitations.
So that, as I said, that's still quite a high number, 74, but this was quite a quick exercise.
And yeah, so we're treating it really as a way of gauging the relative benefits and to think about strategies rather than making sort of hard predictions about energy consumption. So, for example, because passive house isn't a dynamic model, it's possible but tricky, and maybe in this case a little bit questionable to model intermittent use of the air conditioning, which would be quite likely in this case, particularly if it's used as a sort of dormitory, so we'd only be cooling overnight and maybe not every day, for example. That's kind of harder to model accurately in PHP. I'm a bit concerned about the way the roof gains work. So again, it's quite a rough and ready model, and I've just sort of made some guesses as to how that complex physics that I described is actually pans out in terms of a sort of a simple U value, I suppose. So I think we need to do some more work around that, or use a different piece of software to get a better idea of what's really going on there. And similarly, you're probably not going to get a terribly accurate estimate of this sort of benefit of night cooling, especially given that we're talking about a sleeping space for this exercise, but how that works across a whole building or for a different type of building, I think that's certainly worth looking into in more detail. Next slide. Insights, recommendations. Thanks. So as I said, the delta T, the air temperature, that difference is lower than we have, which is kind of helpful in some ways. But yeah, the solar gains are really what's sort of dictating a lot of that sensible loading. But as we were saying, yeah, humidity is a big deal. So yeah, we really need to think carefully about air tightness and VER, and that gets quite tricky, particularly in this sort of mixed mode sort of situation. So if we have different zones, but also if we're using the mechanical systems at certain times of the day and what's during certain seasons, and how those transitions kind of work, and yeah, that needs to be quite carefully communicated, because that will potentially reduce demand a lot if the systems are just off. But we need to make sure that the people using them understand that, and they need to be closing the windows and things like this in order to get as much efficiency out of that whole building system as possible. So yeah, the final kind of observation there really is that again, the Passive House Institute have done a lot of work on this, and I haven't had time to really digest too much of it, but these very high humidity loads seem to be a serious challenge for Passive House, particularly where in a building like this where it's quite densely occupied, because it's a house for 10 children, but we're only talking about half of it, so the floor area against which we're sort of normalizing is quite small. So we're pushing a lot of air through a space with a very small floor area, which sort of upsets our sort of Passive House criterion, which are based on German sort of living spaces at 35 or so square meters per person. We're quite a long way from that here, but even so, yeah, getting down to that 15 looks like it would be a challenge, purely because of the energy involved in this amount of dehumidification. Next slide. Constraints challenges. So one of the things that we said at the beginning was that the building is designed to be intentionally quite leaky, so that could be a bit of a challenge in terms of then retrofitting it to be quite airtight, but we have used fairly well defined openings in terms of the doors and windows and our stack vent sort of opening, but on the other hand, we don't necessarily have access to a lot of the products and materials that we do in the UK in terms of tapes and things. So there's a much more constrained palette of materials for doing things like airtightness, especially. So and there's other issues potentially associated with that as well in terms of the labour. So broadly the selection of insulation and design of how that's integrated is potentially quite challenging. So again, things that we don't really have to worry too much about in the UK are things like supply chain. So there's the available materials are very basic compared to what we have access to in the UK. People aren't there's not the labour that are used to dealing with some of these materials. Critters, also bugs and of various sorts are and other animals a real issue to be aware of. So termites, for example, will go for any woody kind of products. This moisture thing that we've been talking about. So how do we control the humidity in a way that's not going to lead to other problems if we just do the sensible cooling. And I guess another one is the thermal mass exposure. So that's linked to the moisture in the sense that when we're doing cooling, the sort of different pressure gradients are sort of the opposite to what we'd have in the UK. So whereas in simple terms in the UK, EWI is less risky on paper at least than IWI. It's sort of the other way around in these cooling climates, which means that we would prefer, in terms of moisture risk, our preference would be to put insulation on the inside, but that means that we're separating our blockwork walls from the inside, so we don't have that thermal mass, which may or may not be useful for heating. Next slide.
Okay.
In fact, I think we've sort of we've talked about most of these things. Let's just skip that one.
Okay.
Next slide. Mechanical cooling.
Yeah.
So I sort of alluded to this, but it turns out a lot of air conditioning systems, certainly those that are sort of available in Europe, are designed around sensible cooling. So not really any latent cooling or condensation is sort of incidental and it's not really a designed part of or a designed function of the system. And we have identified one product that Alan found that might be better for this, and we're sort of yet to explore availability in Tanzania and things. But there are technical solutions there. Multi-splits or mini-splits is just whether we have cooling in each room, which would be obviously preferential. I already talked about user behaviour. There's a few challenges there. So one thing that some people have pointed out is that once people have the cooling, even if we've designed it to 28 degrees, they might turn it down to 18 or something. We don't necessarily have control over that. But I guess the same applies in the UK. We design a passive house to 20 degrees, and it would be certified, and no one's going to take away the certification if the occupants turn it up to 30 degrees for heating. Interesting kind of conundrums there to delve into as well. I think that is the last slide.
Yes, it is. Okay.
There we are.
Well done, Toby. You recovered well under very difficult circumstances. Okay. Last question, actually, I think probably I could sort of cover. Kate de Selincourt is asking, could we have a bit of background about the buildings people tend to live in this part of Tanzania and how comfortable they are or aren't without additional cooling? Now, that is a good question. What I will do is, I might not be able to do it now, but I might be able to flash up a picture of exactly that, because as you recognise, this multi-occupancy building in the eco village is not the same sort of shape and form as what the people in the neighbouring villages are living in. But we are working with a local school teacher who has half finished building his own home. They're living in it, but he wants to finish it off using the features that he's seen in the eco village home. So we've actually we've created a 3D model, and when we can secure a bit of funding, we'll do some modeling of the house. But we're pretty clear how we would adapt the traditional homes that they're living in line with House 5 features. So that's actually really interesting, and there's a lot of scope actually just to tweak things in that design. So I'll try and come back to that at the end, Kate. Okay, Camilla, did you think about putting the kitchen in separately so that the heat did not affect the building? Yes, in fact, the clients went through a process with the mothers on site, and they did agree. Actually, they prefer cooking outside in a dedicated separate area. But the last trip I was there, they seem to have changed their minds. And now we had designed the house to allow for a cooking area. And as I said, that was then we left that area in, but they weren't going to put the kitchen inside. But they actually changed their minds. And it was associated with I think they realized that the wood cooking was actually very damaging to their health. Or it was miscommunication between the people on site and the management. I think probably a bit of both. So they've decided they do want to use the LPG cooker, which is the current alternative. They can get hold of simple induction hobs. In fact, the school teacher has a microwave, an induction hob, and a gas cooker, so that if there are power cuts, which there are power cuts, and this is an important point, they could use he can use gas for cooking. So yes, we've gone back to the plan where there is an LPG gas cooker in the building. I think when Toby looked at the heat gains associated with that, it wasn't that. I don't think it was that significant, but that's the answer to that question. Camilla again has asked, is the mosquito mesh in the windows? Yes. So we worked with colleagues. Some of you might be familiar with the Star Homes, another experimental building project in Tanzania. And we had a webinar on that. Now, that project was based on natural ventilation, natural shading, and insect protection based on research into the behavior of mosquitoes. They actually came up with a 2-story solution for that home. This is single story, but still raised up off the ground. So simple answer to your question is yes, everything has insect mesh in place, which does affect the ability of air to move across the building to some degree. But it is in a it's 30 acres, this site, and it has a rather swampy area in it. So even though East Africa is just coming out of a 10-year drought period, when we first visited, there were a lot of mosquitoes there. And then they sort of disappeared, not many mosquitoes, but now this year there's been flooding, as you may have picked up on the news, and the mosquitoes are back. So it's a particularly vulnerable site for that. Jana Bolt is asking this whilst you're working out the technical problem. What would be the comfort set temperature and humidity for interior comfort in hot and humid climate for more westernized areas? Wow, there's a lot in that question. Huh. To repeat the question?
No, I caught that. Yeah, what are the comfort criteria for Westerners in Africa? Yeah, how long is a piece of string, I guess, is the cop-out answer. The 28 degrees we sort of came up with sort of based on just sort of conversation and drawing on Andy's and Hida's experience out in Tanzania, and Hida's experience of sort of living in Sudan, and yeah, the set points that people use when they have access to air conditioning. As we were sort of saying, that film comfort is a sort of complex beast, particularly where in these kinds of climates. So it sort of depends on all these factors that we mentioned this afternoon. So the airspeed, the clothing levels and things. It's pretty tricky to boil it down to one number. And one of the things I think that would be really interesting to do once the children and the occupants have been in the building is to do some surveys with them to sort of compare their experience with these numbers that we've kind of plucked out of the air, not completely out of the air, but
no, there's a bit more to it than that, I think. I mean, we did talk to quite a lot of people in various countries, including Pakistan, for example, in Sindh, which was incredibly hot and humid, talking to people about what they would consider comfortable as to whether they would turn the aircon on or not, or what point they would turn it on. When you stay at a hotel, I think a number of countries are actually limiting the settings on aircon. So I think there's a league, and I've noticed in Tanzania that it's 25. And the remotes have been removed from hotel rooms. So I think 25 could be an answer to Yana, because it's being imposed for energy efficiency reasons and grid capacity reasons. Okay, I'm going to carry on with the questions. Tim Wilcoxon has said, what are the traditional ways of cooling buildings in Tanzania? Why was the metal roof necessary? So I'll work backwards on that. So we decided we would basically, when Adele and I were talking about this right at the beginning and chatting with Alan, we tried to keep it materials agnostic. So we just basically looked around, went around the local villages, talked to people to see what they were doing. And basically what they're doing is locally produced sandcrete blocks, timber, occasionally a bit of metal structure, and very thin metal roof sheeting. And that's it. That's what they do. There's very little thatched roofs anymore. They're restricted for like covered areas outside restaurants for tourists, or a very thin grass roof thatch is used for the kind of the first structure that people put up when they start their self-build plot. So most of the housing is managed by people themselves, doing some of it themselves, and hiring local builders to work with them to do that. That's the main route to housing. So there's an initial structure put up, which is very rough, wattle and daub, a very thin grass thatch, and whilst they're building their main house. So was the metal roof necessary? Well, to be honest with you, there's not a lot of materials available apart from metal. And that is basically what people are using, what they're familiar with. And so that's where we started. That answers that. Traditional ways of cooling buildings. Well, the climate is not so harsh, is it, Toby? I mean, it's not you know, Iraq, an urban area in Iraq, or the southern part of Pakistan, Sindh, for example. It can become uncomfortable, particularly when with the humidity, high humidity and high temperatures, and when the wind is low. So people do get hot in their homes, and there are some subtle things going on as well. So, for example, the half-finished house the school teacher is living in currently has no glass in the windows. It has monkey mesh and it has some insect mesh, and it has some very lightweight curtains. Now, those curtains flap around in the wind, and to some extent don't really block the air movement. It's keeping them cool. The next stage, though, is people put in glazed windows. It becomes a lot hotter then, even when it's half open. There's sliding windows with insect mesh, Chinese made aluminium frame things. So that is actually then makes the building more uncomfortable. Then curtains come in, and with wealth comes heavy curtains. So heavy curtains then are a status symbol, and that really is the nail in the coffin. Then that home becomes really uncomfortable. So you say traditional ways of cooling, you're probably harking back to a period which isn't relevant anymore, because the natural materials aren't available and people don't see it. They see it as backward and won't build it. Right, question for you, Toby. Camilla's asking, reducing the solar impact on the roof. Did you think about having a ventilated layered roof to encourage air movement upwards over different leaves to manage the solar gains? Not sure that would work, but intuitively seems attractive. So I'll just answer first and then you can comment. the point of that roof, Camilla, is that it is a fully ventilated roof. So it is a layered roof in the sense you mean, because air can enter at the eaves, and it is removed from the split section at the top of the roof. Now there are solutions that people are trying in places like South Africa, where an existing shack with a corrugated roof may then have battens and another layer of corrugation laid over the top, which is clearly a layered roof. Toby, do you have any sort of experience of that more basic, cheaper approach? Principle.
I don't, but I think this is an area that, yeah, I feel like it's slightly an interlope here, because I think a lot of other people have looked at this in a lot more detail. But I think for the work we're doing, it'd be really interesting to dig deeper into that and to understand more about the physics of the roof and how, sort of sensible kind of layering could help reduce that radiance. But I think an important thing to get your head around is the radiant bit is probably more important than the sort of convective bit, and sort of just trying to deal with it by ventilation is only part of the issue. So, for example, it's almost a swear word amongst sort of AECB and passive circles in the UK, but maybe there's a place for multifoil insulation here. For example, I mean, I'm not saying that there is necessarily, but it'd be an interesting thing to look into and explore to see if that's a way, a project that could potentially be imported or made locally to.
Yes. Thanks. There is an organisation called MEERS, MEERS, which is Mirrors for Rebalancing Energies. What is it? Mirrors. Rebalancing Earth's energy balance, basically. I can't remember the exact order. In essence, they are highly reflective types of roofing which can be added to existing buildings, or even creating canopies to put over agricultural areas or reservoirs and so on. So there's very interesting work going on there, which is basically focusing on managing solar radiation onto areas and into spaces. So kind of moves a bit to Mike Mann's question. Have you looked at PV as roof shading and power? We did originally think about that and look at that. The reality of energy use in Tanzania is there is very limited energy use. They don't consume hardly anything. Lighting, laptop charging, phone charging, occasionally a television, but they don't consume very much, basically. So the pattern that we've seen over there is a very small solar panel powering a battery on a house, and we're talking about a tiny panel, 0.5 meter by 0.5 meter sort of thing. So there is a high capital cost associated with that, and there is no financial structure in place to do that. The idea of community-owned solar farms, small solar farms, does seem like a very attractive idea, but it's not happening as far as I know at the moment. There's a lot of investment with Chinese help into hydropower, for example, towards growing the grid. Okay. Okay, this is another complicated one from Jana Bolt. Would you be able to summarize the best design principles for U values, internal comfort, temperature, and humidity and ventilation, again, more for westernized areas, Westerners living in Africa? I think the answer is yes, maybe, but it's like a book or it's our Cool Buildings program. This sort of thing is what we intend at some point, if we go ahead with this Cool Buildings program, will come out of that program. So that's actually asking for quite a lot of information, and this is kind of what it's very particularly the sort of questions we are wanting to answer. So in time, yes. Mike,
another thing there is Africa is kind of a big place, but there's a lot of climate kind of variation.
Yes.
So Tanzania is particularly humid place, and there's very dry places, and the strategies that are best suited to those different climates are quite different. And so, but it seems reasonably clear that for Tanzania, if you're one option which seems to work reasonably well at the moment is this highly ventilated building, so free cooling, highly ventilated. If you're moving towards a more sort of mechanical solution, then it's air tightness, enthalpy recovery, and solar protection.
I think I've just been reading between the lines of Jana Bolt's question here. I'm guessing, correct me if I'm wrong in the chat, Jana, but I think you might be thinking about moving to Africa. No, I kind of answer in a slightly different way. I've been several times to House 5, and I'm very sensitive to heat and humidity. I don't like it. When there's a nice firm wind blowing, it's great, it's nice. But if the wind drops too much, it really is a bit too much. But I've always found the house very comfortable, this naturally ventilated house with no insulation, just based on shading, air movement, and I found it very comfortable, and I spent a night there, and that was very comfortable. One thing we haven't really mentioned is there is an adaptive comfort method, which is basically just turning a ceiling fan on. So if the wind drops and there's not enough air movement to sort of carry a sweat away and cool you down, you turn a ceiling fan on, which is lower energy than an air conditioning unit. And we've actually sort of played around with that a bit. So in the bedrooms where the bunk beds are, we've changed it from a ceiling fan to two wall-mounted fans, so the air movement sort of cuts under the bunks rather than create a wind shadow for the person in the bottom bunk. It's also safer given the height of the ceilings. Okay, still 23 doughty people listening. It's impressive. Okay, Duncan Bell. There is much research on high reflective paint, even reflecting long wave 8 to 14 micron radiation, capable of lowering roof temperature below the ambient air temperature. So a couple of things there before I pass it to Toby. So every night, our data loggers indicate that condensation forms on the underside of the metal roofs at about the same time in the early hours. And when we visit there, we can see that's exactly what is happening, that the radiative cooling of the metal roof at night time creates condensation on the underside, very small droplets, and you can see the pattern of those droplets on the dust of the plasterboard ceiling. So we know that is going on. And I've just sent, I don't know if you had a chance to look at it, Toby, a sort of a new paper looking at a new product based on a biomass resource for creating kind of bespoke materials, which are trying to answer this question, which I think you need to talk about a bit more. What are the characteristics of the perfect cooling roof? But this paper I was reading suggests that it could cool the space below this material by 16 degrees, which on the face of it sounds like really high, really? I mean, our building is about 5 to 6 degrees cooler than outside temperature, which is a pretty good result for basic materials. But this is suggesting that with the right design material on the roof, you could reduce temperatures below by 16 degrees, which strikes me as amazing. And obviously, I don't know what you think of that, Toby. Is that sound even?
To be honest, and this is one of the things that's been really fascinating about this little project and this exercise is that the physics that we're talking about is so different to the normal building physics that we sort of deal with, passive houses in the UK. It's been sort of a real kind of intellectual stimulation and really sort of fascinating to sort of get into that in this sort of depth. That said, I don't know a great deal about these kinds of things, but that is an obvious next step with this whole thing, is to start to unpack some of these things and look at these technologies, and the kind of paints that Duncan's mentioned, for example, and to understand more about how one can design a roof that takes advantage of all these effects and technologies. I guess one reservation that I might have is I guess the sort of the commercial aspect of these things, are they sort of patented Western products that are going to be very expensive to apply in places like Tanzania? And if so, are there more kind of lo-fi options that we can get to perform maybe not as well, but well enough? So yeah, probably all I can add.
Well, there's a certain amount you do with white paint on a dark roof. I mean, the school teacher's house is actually a black metal roof, and a common color for roofs is a nice deep blue color, which is lovely, but clearly is counter to what we're suggesting in terms of reflectivity. Okay, so Malcolm Johnson is asking, so is it recommended that open lattice window openings should now be sealed, glass fitted, to minimize warm air ingress? So the work that Toby did with PHPP was an assumption as to was focused on what would happen, what would we have to do to the fabric to manage the running costs of an aircon unit. And then Toby sort of realized all that sort of stuff about sensible and latent cooling, and dehumidification actually is the key thing there. But at the moment, the building works well with the windows left as designed, so basically open to airflow. It would only be necessary to put glass in the windows once you take some or all of that building to a mechanically conditioned space, which could be as simple as single glazing, maybe a relatively thin layer of IWI, which is what Toby was looking at, internal wall insulation, and a little bit more, but still nowhere near passive house levels, U values for the ceiling. So Toby was basically trying to explore for us the relationship between the fabric and managing the running costs and the energy use of the aircon unit. We haven't got into the carbon intensity of that at the moment because it's a Tanzanian grid, and that would be a later step to sort of try to understand how carbon intensive that is and how that would impact what we should be doing there. Do you have any comments on that, Toby?
Nothing to add really.
Okay, cool. Okay, Alessandro has asked, well, he's stating it. Oh no, it's a question. Capital letters. Therefore, previous passive house principles in hot and humid climates are not applicable anymore, question mark. Only air tightness, aircon and MVER are necessary. I think the principles are building physics principles. If what you're saying is, maybe you're asking, does passive house, the passive house standard as applied to hot and humid climates, is that what we should be doing? Now, we do have a bit of a view on that, I mean, obviously you can see that this has opened a lot of discussion and debate, and people can get very worked up about some of the sort of things that come out of this conversation, because a move of buildings towards more tightly controlled environments carries a lot of stuff with it. There are two really quite different directions here. It's almost a subject of another webinar, because you will create different communities and completely different spaces and environments if you take one route versus another route. The pressures of modern life do seem to be pushing always towards closed-in living environments, security, pollution, noise, the perception of wealthy Western, approaches to things being adopted. So the forces are generally away from the sort of thing we're trying here. But is that sustainable? Well, clearly in many ways it's not if they're badly designed, reliant on aircon with a world full of power cuts. They're quite dangerous, potentially quite dangerous buildings to be creating with an uncertain power supply. So if everybody was able to build a passive house and run their aircon at some sensible level, that could be some future scenario, but it just doesn't seem like it's possible because the supply chains are not in place, the costs are not, the countries are too poor to invest in this level at scale. It just doesn't seem feasible that will happen. What is going to happen is something in between, which is not good. Badly designed buildings with emergency aircon, which I think you mentioned in one of your slides, Toby, didn't you? Did you call it a distress buy or something?
I think I might have taken that one out. Yeah.
Oh, distress purchase. I thought it was a term you used.
Yeah. So yeah, yeah, in the middle of a heat wave, yeah, everyone rushes out to buy air conditioning, but the building's not very well adapted for that.
Yeah. I think Alessandro says he we live, design and build in Singapore. Is there a passive house? One of the few certified passive houses in hot and humid climates in Singapore. I think there might be. Okay, well, do stay in touch, Alessandro. We'll be doing this sort of with less technical problems, more webinars on these topics. Let me just have a quick scan ahead, see how many questions there are. There's a good number of questions. Obviously, this is a special webinar because we've gone on way beyond our usual time, but I don't see. Michelle, are you happy we just maybe take 2 or 3 more questions?
Yeah, I wouldn't go much past 1:45, if that's okay.
Yeah, I think that's sensible. And people can just disappear. Of course they can. That's fine. Okay, I'll just pick out maybe 3 more. There's a quick question about PV panels and hot water. Well, the hot water use again is incredibly low, and the water comes into the building at about 30 degrees. So you don't need to heat it for showers. Hotel rooms do have hot water boilers in them to heat for showers. So I guess again, at some point, as people get wealthier or their job prospects improve, bring on more income, they might put a electric hot water boiler in and use it as and when the power's available, I suppose.
And then the kind of solar thermal hot water systems that you see sort of in Spain and things, I guess, would be a logical solution then. But
Yes.
In terms of the impacts of the performance of the roof there, I mean, they're relatively small panels because you just don't need very much energy to provide that. And yeah, when you've been sat outside in 35-degree heat all day at 80% humidity, the last thing you want is a boiling hot shower.
Well, I think what you do see outside the people's houses, you'll see a sort of concrete block sort of base, which can be quite high actually. It can be like 2 meters high, and then a very large black plastic water container, which is well, particularly where there might be a borehole, which is relatively or this has been provided publicly. In the Eco Village, they have boreholes because the charity's invested in boreholes, so they have pressurized water, which allows them to do this. So those large black water tanks, which tend to feed toilets and showers, are heating up in the way that you see in Greece and then Spain, which is why the water is coming in at a comfortable temperature to the bathrooms. Okay.
The EBGBs on the Legionella front, but
I know, I know. Yes, indeed. Duncan Bell, in these hot countries, is not earth-sheltered buildings a solution, as in North China? I'm sat in an earth building now, very cool. Earth building is good, but I think in terms of Tanzania, so we dug, when Adele was over there, we dug some trial holes and we measured we were looking for the water table, which is at that time was 1.5 meters down. And we took the temperature of the sand down at that level. It was 30 degrees in the sand, down at 1.5 meters deep. Now that was in part of the site which didn't have tree cover and vegetation. Where they've replanted trees, that is a lot cooler in that area there. So I suspect you would have seen now if the annual average temperature in Tanzania is about, I think from memory, it's sort of average, something around the 26 mark at the moment.
I'm going to have to get the door.
Okay. The ground temperature is going to be around that sort of temperature. So where the building site was, if the ground is 30 degrees, as a sort of annual average, that is not very cool. Combined with the humidity issue, you really do want to maximize wind pressure across the building. So putting the building in the ground, maybe you could design it to work okay, but I think you take the point. Different climates have different building solutions. Okay. Duncan Bell, what about foliage, sheltered trees and ivy? So again, coming back to this thing that we will be asking them to, well, they want to do this anyway, to plant trees around the house in order just to sort of do further shading further out from the house footprint. The overhangs on the house about 1.5 meters at the verges and 2 meters on the eave, so it's heavily shaded. But as I said, when you go into the sort of forested areas, it is a lot cooler under there. So basically we bring trees in around the building, we should be cooling the environment around it, which is no doubt going to have a cooling effect on people in the cooling the air that's moving through the building. However, we don't want to do so much that we actually block air movement and it becomes, again, stiller, more humid air. So it's a balance. Let me just find one for you.
I
think we're probably there, actually, to be honest. Yeah.
I was going to say, just in response to the earth sheltered building, I think you sort of more or less said this, but one of the things that's important now is basically the annual average temperature. So Tanzania's got a pretty stable temperature. I can't easily put it up, but yeah, I showed that graph there where it's 30 degrees plus or minus a few degrees most of the year, which means that at depth you're going to have very high temperatures in the soil. So it sort of fluctuates near the surface, but once you get down to about 2 meters or so, it's basically the same as the average air temperature. So if you've got very high average air temperature, then you're not going to have a terribly cool ground to rely on.
One of the things that we did,
seasonal rather variation.
We were questioning whether there was any significant advantage in lifting the building off the ground and allowing ventilation under the building with a thermally lightweight floor. The way that it's built is the way that contractors build everything. So, it's difficult enough to get something built just slightly out of the ordinary. So we felt it was structurally, it would have to be a structural frame rather than mass masonry. So we felt we were pushing it too far. But Toby, do you think from what you've done so far, could you see a dramatic advantage or not in decoupling the floor mass? To some extent, we have decoupled it because it has this big mass of coral-based rock, which is full of air. But do you think it would be worth considering some sort of suspended floor and allowing air movement underneath or not?
It probably wouldn't make a huge amount of difference one way or the other, particularly if we could have something a bit more in line with regular insulation. So from a thermal performance point of view, it's probably not too important. I was just thinking about that paper that you circulated our group a little while ago about the height that mosquitoes sort of fly and operate. So that was basically saying that mosquitoes tend to fly relatively low to the ground, and if you're able to elevate a building, or I suppose even have a 2-story house would work maybe.
We have a couple of interesting papers in our little Cool Buildings library, which I think it was in Ghana, I think they were looking, or Nigeria, I can't remember now. They actually built a test rig to lift a small building progressively higher. They had one, and they were capturing mosquitoes at different levels to understand how high you had to lift it before you got a marked reduction in entry, and it was round about the kind of height of a person under you could walk under, which I think is why the Star Homes took the bedroom space, living room bedroom space to the second floor. So basically, yes, at least 2 meters high, I think I remember from the paper. Yeah. Okay, right. has been demanding and interesting at the same time. Well done, Toby. That was very awkward to deal with, so I really appreciate that. We've got a few comments saying thanks very much, very interesting presentation. So I think it probably went down well. Watch this space. We will no doubt be doing more on this topic. And as you say, Toby, it is fascinating to take ourselves out of our heating, climate, passive house mindset and apply the same building physics based rigor to these very different contexts and climates. Okay, so thank you, everybody.